So if you're looking at second order systems, this is a general form of second order systems, right? There are four types of second order systems, as I mentioned to you. If you look at this system, the roots are real and distinct. You should understand what real and distinct means. We've already covered this. Such a system is an over-damped system. Okay? The response of such a system looks something like this. Okay, we have T plotted against C of T. Response looks something like this. It's an over-damped system. So you have to relate three things. Okay. First, roots are real and distinct. Then, if roots are real and distinct, you know the system is an over-damped system. And the over-damp you can make out from the response. If you plot them on an S-plane, real, imaginary, what you're going to see is one of them is going to be here and the other one is going to be here. Okay. Type B system is going to be What do you mean by damped? You know what do you mean by damped? Huh? Huh? Hinder, right. Kind of. So when you have a damper, you cannot really drive the system very fast. It gradually just does that, right? So you see that it gradually comes to the final position. So that is the reason it is called a over-damped system. Every system that has roots which are real and distinct will behave in this way, and that is the reason it is called a over-damped system. It is over-damped. It is a very safe system. Okay. So the second one is this. Here, if you look at the response, you have, say it again. Damper, yeah, right. So if you have right. If you have a damper, it just does that, right? So but if it have a spring, it will keep doing that. So if you have a roots, this is an under-damped system. So here roots are complex. Okay. So if you solve the roots of the denominator for this equation, for this system, Malcolm, If you solve the roots of that system, particular system, it is, you see that roots are complex, okay? So if you plot the roots, you're going to get something like this. You have real and you have imaginary. So the roots would be somewhere here. So the poles of the system would be, one would be positive, one would be negative on the imaginary axis. What are you confused of? We're looking at, this is a second order system, okay? This is a general representation for second order system. We're looking at what are the responses of such a second order system. So if the second order system has roots which are real and distinct, it will behave in this way. So you're looking at the response. This is the as time, this is the time scale, and this is the response of the system. So if you apply an input, it is generally going to behave like this. Like if you have a damper, if you just push it, it's slowly going to settle down, right? So that is what you're seeing here. And such a system is called overdamped system. Now, if this roots, for example, in this case, the roots of the denominator are complex. The poles are complex. Okay? If the poles are complex, it is going to behave as an underdamped system. So such a system is not damped. It's going to just do that and then settle. Okay? So for example, if you don't have a damper in this, if it's just a spring mass system, it might behave something like this. This is an underdamped system. So such a system will have roots which are complex. And if you plot the roots on a S-plane, this we did, right? This we looked at in the for the first order systems as well. This is where the roots are. We said this cross marks are going to be used for denoting roots. These are roots or poles. Roots or poles. Again, these are roots or poles. You see, these are on the real axis. They're real and distinct. They're two separate roots. You see that? Okay. So if you're looking at this third type of system, the roots, what are the roots here? Huh? Negative 3i, right? Right? So these, you have to distinguish between complex and imaginary. This is imaginary, purely imaginary, right? This is a complex root. Do you understand the difference between complex? Complex has a real part and a imaginary part, right? This has just imaginary part. The roots are plus or minus 3i or 3j, correct? So if you look at the response of such a system, it's never going to settle. It's going to be marginally stable. It's always going to do that. Okay? So such a system is associated with undamped system. Okay? Now just be careful. Don't confuse yourselves with undamped and underdamped. Undamped is, it doesn't have a damper at all. It's just going to do that. If you supply an input, it's just going to keep doing that. Okay. And finally, so here roots are purely imaginary. The final one, if you have the final one, what are the roots of the system here? What are the roots of the system, of this system? Negative? So it is s plus 3 square. You have negative 3. You have two roots, s equal to negative 3, negative 3, right? So they are real and repeated. Try to distinguish between this case and this case. This is real and repeated. This is real and distinct. So if you have such a system, this is a critically damped system. Okay? Ideally, you want all your systems to behave like this, where the response time. So look at this. The response time for this is really slow, right? It takes time to settle. Now here, the response time is pretty fast, and it's also settling very fast. You see that? You want all your systems to be like this, but it is difficult to design a critically damped system. So any system which has roots which are real and repeated is a critically damped system. Okay, and if you plot this on a S-plane, you have this, and you'll have another root over there itself. Okay, so minus 3, minus 3. The two roots are at the same point. Okay. This one? They would not be in the second quadrant. They would be, tell me where they would be. So your roots are plus or minus 3j. Right. So it will be this one and this one. Plus or minus 3j, right? So one of them will be here, or one of them will be here. That's good. Next, we're going to discuss we'll discuss a little bit more about your general second order system. Okay. So one of the things we're going to define is damping ratio. Okay. This is that symbol is called zeta. Okay. So the damping ratio zeta defined as exponential decay frequency. And this is equal to 1 over 2 pi to the if you look at this system, what do you see in this system? Look at this system and tell me what do you see? No, it is not. It's not. You cannot do that. You cannot have a function which will exponentially increase. Okay. If it exponentially decreases, it just decreases. Right. This is. Do you see something of a natural frequency occurring here? Right. A system having natural frequency. Okay. It's oscillating with a natural frequency. So if you can relate this to this system. Okay. And you can relate something like this or this with the exponentially decaying system. Okay. Now if I just put that here, if you look at G equal to G of S equal to B over S square plus AS plus B, this represents exponential system or exponentially decaying frequency, decaying system. Okay. And we have G of S equal to B square plus b. This is a system with which has output represents a system with natural frequency, something which is oscillating with a natural frequency. If you take the if you just apply this to these two, you'll end up with your zeta, right? It was omega n is equal to root of b, right? So I've just used b equal to omega n square. You can arrive at this using the definition of natural frequency and damping ratio. But I don't want you to think about it now. What is important here is see, we used the general form, we used this, right, to represent the general form. This doesn't necessarily have any meaning, okay? This A and B are just random variables, right? So what you can do is you can represent the general second order system using its natural frequency and its damping ratio. Okay. So G of S is equal to omega n square over S square plus 2 zeta omega n plus omega n square. This is very important. Okay. You see, what I've done is I've just used this to replace B with omega n square and A with 2 zeta omega n. Okay. So if you're given, now compare this and let's say this. Okay. What is the natural frequency of that system? Oh, yeah, 2 zeta omega n s. Right. Now compare system D and this equation and tell me what is, do you see any similarities, or if I ask you to find the natural frequency. Can you find the natural frequency of that system? What is the natural frequency? Natural frequency of system D. Look at system D. 3. So always use this, okay? Don't use the numerator, because you may have a gain in there, okay? So always use the numerator. The natural frequency of that system is omega n is equal to 3 for system D, okay? What is the natural frequency of, what is the damping ratio of system C? Of system C? John? Of system C? It is 0, correct. The damping ratio of this system is 0. See, because there is no damping, it is behaving like this. You see that? Damping ratio is 0 because if you compare system C, because what you do is you do S square plus 9 is equal to S square plus 2 zeta omega ns plus omega n square, right? Okay? You can also do this. You can say S square plus 0s plus 9. Okay? So what is, if you compare the coefficients, omega n square is 9. So omega n is 3. Zeta is 0, right? Because 2 zeta omega n is 0. Omega n is already 3. 2 cannot be 0. So zeta has to be 0. All right. So you see, if the damping ratio is 0, this is 0. This is some value. So you see, the system is going to behave like this. All right. So your question could be something like this. Example would be find omega n and zeta of g of s is equal to 36 over the square plus 4.2s. Okay. This is a very simple question. All you need to do is figure out omega n and zeta. You may get significant points for this. Not this exam, but midterm. So don't cough up on this one. It's a very, very simple question. Okay? Any doubts until now?
Is that 42S?
4.2s. So what is it? Natural frequency of that system? Right. What is the damping ratio? 2 times 6. It's not 2 times 6. 4.2 over 12, right? Because what you're going to have is 2 zeta omega n is 4.2. 2 omega n is 12. So zeta is 4.2 over 12. Right? You with me? Okay. Hmm? 2 times 6 is 12, right? 12 times zeta is equal to 4.2. So zeta is equal to 4.2 over 12. All right. So the next part. So we have already defined 2 parameters associated with a general second order system, right? What are the 2 parameters? Right. What are those? What are those called? Huh? Right. What are the parameters we have defined for a second order system? What are those called? Those are the notations. Huh? Okay. Did you see it here? We're going to define more parameters. See, we defined something called rise time, settling time, right, for the first order system. We're going to take a look at underdamped system and parameters. See, in most cases, you're going to see a response which looks something like this, underdamped system. That is the reason we study, Malcolm, you need to keep your cell phone here. You want to keep it? In most systems, we are going to take a look, are going to behave like this, okay? That is the reason we are going to study such a system. You very rarely going to get a system like this, although you want a system like this. Now you don't want a system like this, right? Because it can go unstable. See, a little bit of here and there, it may start doing that. Okay? And this system, again, whatever we discussed here, you don't want such a system as well, unless you are looking for a really robust system, okay? Very safe system. So underdamped system and its parameters, when we do that, what we're going to look at is, we want to plot this is your time scale, and this is your response. Okay. Note, see, keep a note on what is your y-axis. It is C of t everywhere. Okay. So whatever you get, for example, what is C of t here? What is C of t for this system? What is C of t for this system? If R of S is equal to 1 over S, what is C of t? C of t would be Laplace inverse of C of S, which is equal to 9 over S into S square plus 9. Okay, Laplace inverse. So you need to do the partial fraction expansion and figure out a response. That would be your C of t. So everywhere this is a time response. Keep in mind this is a time response. This is not frequency response. So whatever you get, whatever C of S you get, that is a frequency response. You only when you take the inverse Laplace of that, you're going to get time response. Clear? The frequency response, or what is the frequency response of this system? Huh? That is the system. That is not the whole expression. Try to differentiate between the system and a response. You're going to get a response only when you apply an input. What is the response of this system? This is the system. Okay? This is the system. So if I ask you to find a response of this system, the frequency response of this system, the first thing you have to ask me is what is the input? If I tell you the input is a unit step input, that means R of S is equal to 1 over S. You substitute that, okay? So C of S over 1 over S is equal to 9 over S square plus 2S plus 9. Which implies C of S is equal to 1 over S 9 S square plus 2S plus 9. This is the frequency response. Now what is the time response of this? Laplace inverse. C of t is equal to Laplace inverse of C of S, which is equal to Laplace inverse of 1 over S 9 S square plus 2S plus 9. Got it? So So whenever you're asked a response, you have to follow the steps. You'll be given an input. Whatever this represents a system, whatever is in that block. So only when you're given the input, you can find the response of that system. So if I plot the response of an underdamped system, all right, let's take a look at this. So do you see this as the peak? This is your C of t. The y-axis is C of t, x-axis is t. This is C max. This is figure 4.14. This is C max. Do you see this as C max? Maximum response. Okay. This is C final. You see, this is a final, right? Wherever it settles, that is a final response. This point is 1.02 times C final, or 2%. Okay, and this is 0.98 times C final. This is 0.9 times C final. This point. Are you clear with this? So everything you define with respect to the final. Whatever the final response, you see, you first define the max. Max is peak, right? Maximum response. So, Malcolm, how many times are you going to make me tell you that you cannot do that? You cannot keep doing that. See, this is just 2% of the.
Does that show all of that?
Yes, it shows all of this. Okay. So you have 2% of the final, 2% less than the final, and this is the C final. This is C final. Okay. This time, now you see this time, right? It's called the rise time. So how do we define rise time? Sorry, not this time. Let's define this. How did we define rise time for the first order system? 0.1, right? Do you remember 0.1, not 0.2? So this is 0.1 times C final. Okay. So this is the rise time. Time taken by the response to reach from 10% of the final to 90%. So you see, this is 10%. You note down the time here, and this is the 90%. And you figure out what is the time difference. This is the rise time. Simple. This is your peak time. Understand? Peak. Time taken to reach the peak, the maximum response. Okay? And what is this? Settling time. Okay. So settling time is the time taken for the system to reach within plus or minus 2% of the final value and stay there. Okay. It's fairly simple. See, look at this from a system you are designing. Okay. So you want, if you're looking at a system you're designing, what kind of rise time do you want? The time taken for the system to reach 0.1 to 0.9% of the final value, or 0 to 60 in many cases, if you're designing an automobile. Okay. Peak time is, right, it depends on what kind of automobile you're talking about. So it actually depends on what kind of system you're designing. This could be 2%, this could be 5%, but for this course we are going to take this as 2%, plus or minus 2%, not 2%, plus or minus 2%. So it will be 4%. Huh? Huh? Formula is? Yeah, we'll get to the formula. We'll get to each of the formula. But try to understand these parameters. There is Cmax, there is rise time, there is peak time, there is settling time. What do these mean? So you understand rise time, correct? The peak is the maximum value it reaches. All right? The time taken for the system to reach that maximum value is the peak time. The time taken by the system to be within plus or minus 2% and stay there. So for example, if it reaches, see here it reaches 2%, right? But we don't use this as the peak time, settling time, because it doesn't stay there. Here it reaches that 2%. But it is not staying there. But once it reaches this point, it stays within that plus or minus 2%. It doesn't move, it doesn't go out of that plus or minus 2%. So the time taken for the system to reach plus or minus 2% and stay within that plus or minus 2%. Yes. It's okay. That's okay. So you're going to see that in any system. You're never going to see it tracking that. Okay, it's going to do a little bit of wobbling, but that's okay. If you, for example, if you zoom in on this response, you're going to see that oscillations. But if it is, as long as it is within plus or minus 2%, and that 2% you define, it's up to you as to what percentage you want, right? If you're designing very, very precise systems, you may say, I need 1%. You may say, I need just 0.5%. Or if you're okay, you may say plus or minus 5%, plus or minus 10%. But for this course, we are going to use plus or minus 2%. All right?
Just to go back over, I think you talked about last class, so like, say that we were designing a fire station case like that airline.
Mm-hmm.
It was shorter rise time for the spider,
Smaller rise time for a spider jet.
higher or like less percentage of that stuff.
Right. You actually need shorter rise time as well as shorter settling time. So you have right, right. That time you have to really critically design your system such that you get both very good response time or very good rise time as well as very good settling time. You could design such a system, but it depends on what you're going to compromise. You're going to compromise a lot of fuel. You're going to compromise efficiency. You want an effective system, right? So there is one more term. So I'll just list the terms and give you the formulas. So rise time again. It's 0.1% or 0.1 to 0.9, 0.01%, 0.1 to 0.9 of final. TR, it's we'll use a table for this, okay? And this table will be given to you. Table figure 4.16 to find the rise time. Peak time TP will be equal to pi over omega n into root of 1 minus zeta square. Okay. This is 1, 2. We'll define something called percentage overshoot. So percentage overshoot is quite simply the maximum. This is that percentage overshoot. This quantity, okay, over the final. You understand that? Percentage overshoot is how much times the final is it going over the final, okay? So if you look at percentage overshoot, the formula is e to the power of minus zeta pi root of 1 minus zeta square. Okay. And finally, your settling time is 4 over zeta omega n. Okay. And this 4, see, this formula is specific to plus or minus 2%. If you're talking about something else, this formula will change. Now we can derive or we can arrive at these equations, but I don't think that is really we won't do that. It is not quite in the scope of this. If it may be in the scope of this course, but we are not going to do that. If you want to do it, or if you want to know how we arrive, how we get to these formulas, you can always just refer to the textbook. And if you want, I can explain it to you how we arrive at this system, these formulas. Now, what you need to do is listen to me very carefully, okay? With regards to exam and assignments, when it comes to, and this is my observation, if you're asked to calculate any of these, you may be okay. You may just substitute and figure it out. Now, if I say calculate the natural frequency and the damping ratio, given the rise time and peak time, or percentage over and peak time, you stumble, you don't know what to do. So if I give you peak time and percentage overshoot and ask you to find the natural frequency, what are you going to do? You're going to use this formula. Use this formula, okay? Substitute TP here. So you see there are always two equations and two unknowns, right? So you should be able to figure out the natural frequency and the damping ratio of that system. And the reason this is important is, if you're doing an experiment, right, you supply an input to a system, you can very easily figure out settling time, percentage overshoot, peak time. You can just measure those, right? And you can figure out the natural frequency, the damping ratio of that system. Natural frequency and damping ratio. You see what I'm saying? The reason it is important is, you can very easily find the peak time. If you subject a system to an experiment, you supply an input, right? If you look at the spring mass damper system, if you just push, that is the input. Now, if you do a plot, you'll know what this peak time is, you'll know what this rise time is, or percentage overshoot is of that system. Once you know that, you don't have to do a physics experiment to figure out the natural frequency or the damping ratio of the system. You can use this formula to find those, right, which are very important to that system. Once you know that, you can design around that system. You can control that system. You can design your control system around that system. Okay? This is also going to be important for your lab, pre-lab specifically. So today's pre-lab, have you attempted the pre-lab today? No? Okay. So make sure you attempt the pre-lab. I think you have enough material to attempt the pre-lab. Before you come to class today at 2 o'clock, do the pre-lab. Yes. It comes from, I can prove to you, here we cannot prove, but for first order system we can prove that it comes from 0.1 to 0.9. Say the thing. It doesn't start from 0, it starts from 0.1. Peak time starts from, yes, right.